Well, first of all, thank you very much for the invitation. I'm a newcomer to this field of magnetic materials. So today I'm going to talk about, some latest story from my group on engineering new magnetic states in twisted two-dimensional magnets. First, let me acknowledge my collaborators, Professor Kin-Fan Mak at Cornell, and the group members who have contributed tremendously to this project, particular postdoc Yang Shi, who's joined Institute of Physics in China recently, Shenwei Jiang, Tingxin Li, and former student Zefang Wang, and current student Li Zhong Li. We got our bulk crystals, in this particular case, chromium iodide, from Josh Goldberger's group at Ohio State University, and hexagonal nitride crystals are from National Institute of Material Science, Japan. And the TEM work was done in collaboration with my colleague, David Mueller here. Okay, so I'm going to talk about magnetic states or magnetic phenomena in atomically thin materials, crystals. So I will introduce a little bit about layered magnetic materials and give you a particular example where the magnetic states are dependent on stacking order, how you put the layers together, and then how we can utilize this property to engineer new states. So magnetic thin films have been around for a very long time, and they're very important materials for technology, particularly for information storage. Claudia has already given a very nice overview and motivation why we should be interested in this type of materials. So we became quite interested in this class of materials, around 2016, 2017. There are two Nature papers reporting the existence of long-range magnetic ordering in materials, crystalline materials, intrinsic, and those are the two examples. So this one is from Shan Zhang's group from UC Berkeley, and this is from Xiaodong Xi's group from Washington in collaboration with colleagues from MIT and Carnegie Mellon. So you have seen Disha's name in Claudia's talk as well. So, so why should we be interested in two-dimensional magnetic crystals? So because those materials are extremely thin, they are highly controllable. So you can, using electrical fields or electrostatic doping or string or making stacking to control their properties and look for new ideas for applications. They are ideal platform to study some fundamental properties. So this, for instance, here we construct a very sensitive magnetic imaging microscope. You can see the fluctuation of spin in real time and study their correlation properties. And you can also easily integrate those ultra thin sheets with other non-magnetic materials, topological insulators or superconductors, So here's an example from our group to marry superconductivity and magnetism in order to engineer new states. So I'm going to focus on one particular class of layered magnetic materials. And actually, the family is very large. So this particular material class we are going to look at is made of transition metal, partially filled d electrons with halides. So some candidates are shown here, red and blue, just to represent different stacking orders at room temperature. Some are just mixed. So I will focus on chromium triiodide in particular in this case. To make a story simple, the way you can think about this material is that it's made of thin sheets, and each sheet you have chromium ions surrounded by iodine. So the magnetic ions make this honeycomb structure, and the structure is, heterohedral, surrounded by those iodine ions, as I said. So magnetism comes from this chromium ions. It has 6 electrons and it donates 3 to the other ion, and you have 3 left. And if you look at the crystal field, it occupies the lowest T2G level. And in this chromium iodide, the spins are out of plane. So out plane is the easy axis. So you can think of this effectively like a 2-dimensional Ising magnet. And then you can stack sheets like this on top of each other. So bulk of this material is ferromagnetic. The Curie temperature is around the 60 Kelvin. And easy axis is out of plane, and you need to apply about 5 Tesla to rotate the spin to the in-plane direction. And what's interesting is that when you exfoliate this material down to 1 layer or 2 layer, they are still magnetic. So what I'm showing here is result from magnetocircular dichroism. So you are just looking at the absorption difference between right-handed and the left-handed light. And the difference you can think of in this particular case is proportional to magnetization. So we measure magnetization as function of out-of-plane magnetic field. And as you can see here, in monolayer, you see this very beautiful, typical MH curve with this hysteresis loop. But if you look at a 2-layer, actually the magnetization does not go up. Actually, it becomes 0. So this is an antiferromagnet instead of a ferromagnet. And then, those two are the potential alignment for the spins. And then if you apply a larger magnetic field, around 0.5 Tesla, then you can align the spins in 2 layers. So this is the spin flip transition. It's first order, and you can also see you can also see hysteresis. Okay, so just from this simple experiment, we can extract the energy scales associated in this problem. So there are 3 energy scales. One, the largest one is the in-plane exchange interaction. So we saw that magnetism survives up to about 60 Kelvin. So if you convert that, so the in-plane or interlayer exchange is on the order of a few millieV. That's 2 millieV. And the other energy scale is the anisotropy energy. We saw that you need to apply a few Tesla to reorient the spin from out of plane to in plane. And that gives us, anisotropy energy on the order of a few tenths of millieV. And then the smallest energy scale in the problem is the interlayer exchange interaction. And we saw that you need to apply on the order of 0.5 Tesla to flip the spin. So this is on the order of 0.1-ish millieV. And as you can see here, the energy scales are very small. And they are also very different, compared to the in-plane intralayer exchange. Therefore, we can manipulate them or control them with external means easily. So in the last few years, we have been quite busy playing with different means to, control or manipulate the interlayer magnetic ordering. So we can apply electric field to switch the interlayer magnetic ordering, or we can using electrostatic means to dope it, to change it, apply strain. And then there are some new application ideas, based on those controllability. But today I would like just to focus on the last point, what the stacking order can help us. So I hope you still remember this slide when I introduced the bulk and the thin film properties. So what's surprising here is that, monolayer and the bulk are ferromagnetic, but once you get down to two layer or field layer, the interlayer interaction changes. It becomes antiferromagnetic. So the question is, how do we understand this? It turns out that this material has two different stacking order. One is called a monoclinic. You can just think of like a shifting each layer by a third of the distance along the A-axis. And there is another stacking order called the rhombohedral, and you shift each layer along the metal-metal bond direction by one unit cell. At room temperature, this material is monoclinic, and if you cool down to about 200 Kelvin in the bulk, it becomes rhombohedral. And that's the side view of those different stacking orders. So D-Shell and my colleague Craig Fenney a few years ago did a DFT calculation to try to understand, this problem, why the magnetic interlayer interaction changes character once you get down to 2D limit. So you can just look at this plot, for example. So what they're trying to show, the blue areas correspond to ferromagnetic interaction dominates between the layers, and the red area corresponds to antiferromagnetic interaction between the layers. And the axis is like you shift one layer with respect to each other along the 100 and 010 direction. So this is some kind of a map. So if we just shift the two layers relative to each other along the A-axis direction, then you will go through stacking order from monoclinic to rhombohedral, to something in between. And you can see that, the interlayer exchange changes sign, and also values are given in this plot. So, and this tells us that, the interlayer magnetic exchange is very sensitive to the stacking order because, we need to include all the nearest neighbor, next nearest neighbor, and also the bond angles, they all change. So, and that could explain why we observe antiferromagnetic interaction when we get down to two layer. So likely that, the stacking order is trapped once you cool down to low temperature. You stay at the monoclinic, which is favored at room temperature. And this is the preferred magnetic interaction. So we did a small experiment to verify this is the case. So what we did is to apply hydrostatic pressure to help the system to go to the lowest energy structural configuration. So what I'm showing here is the magnetization as function of outer plane magnetic fields before we apply pressure and after we apply a pretty high pressure and you release pressure and do the measurement. So for those different two-layer samples, without applying pressure, we get antiferromagnetic ground state. But after you apply pressure, you switch to a different structure order, and then it becomes ferromagnetic as in the bulk crystal. And this measurement is correlated with structure change by Raman, so it's confirmed. And similarly, you see pretty much the same effect when you look at 5-layer or other layer thickness. Okay, so now the question is, we know that magnetic ground states are very sensitive to stacking order. So can we tailor them with a twist? So what I'm showing here is one sheet, and you can see the honeycomb structure for the magnetic ions. The lattice constant is about 0.7 nanometer here. So now I come in with a second layer and I stack them with a little bit of a twist angle. Immediately you will see a moire pattern. So that's kind of an interference pattern between the two. And the lattice constant suddenly becomes larger. On top of the atomic lattice, we have this periodic moire structure. So in this case, for example, the twist angle is relatively small. The moire period is determined by the angle. And for about 2-degree twist angle, the lattice constant here is 20 nanometer. So we get, on the order of 30 atoms, within this unit cell, larger cell. So at small twist angles, we can see all possible stackings emerge, so this is some kind of a AA stacking, and monoclinic rhombohedral, they all come out. And we know exchange interaction is short range. So spatially varying interlayer coupling not immediately emerge by just doing a small twist. And the theorists are quite ahead of us, so they have predicted that some very interesting new magnetic states. So for example, non-collinear texture or even skyrmions. By the way, the skyrmions here are not determined by a DMI. They are due to the different stacking order and the competition between antiferromagnetic and ferromagnetic interlayer exchange interaction. Some magno-moire bands and even networks, and propose perhaps interesting applications based on those. Let's try to see them. So, so here's our experiment. So the idea is straightforward. We first identify a monolayer of chromium iodide, and then you can use the soft stamp coming. Pick up half of it, and break it into two. And then you can rotate the remaining part by a very well-controlled angle. And we can control the angle within ½ degree. And then you put the other layer on top, and then you get this twist layer. And we can see that indeed that this is what we can see. So this is the diffraction pattern from this TEM study of this material. And you can see, because we have 2 layers of chromium iodide, so you see 2 spots in the diffraction pattern. and they overlap, so it's a little bit elongated, and you can reconstruct the dark field image, from each spot, and indeed you see the interference pattern. And to see the real space image, you just need to superimpose, all the three angles together. Okay, so now let's take a look at the magnetic properties. A large twist angle, in this case, we saw ferromagnetic interaction, and that's kind of an image showing you, sample is relatively uniform, so like each line is for each monolayer. So you get a larger magnetization at the zero field in the overlap area. So it's about twice of the monolayer case. And just to remind you, this looks very different from natural bilayer. So how about smaller twist angle? So small twist angle in natural bilayer, we should get, antiferromagnet. And the blue line shows the magnetization in this twisted bilayer. It actually doesn't look like the monolayer response, also doesn't look like the natural bilayer response. It's a little bit of kind of a mixture of the two, because you see here, there's this spin flip transition, but then, we have remnant magnetization at the zero field. So this looks like we have a combination of ferromagnet and antiferromagnet. And by the way, for optical probe, we are looking at the spot about 1 micron. So the image here showing that, we have remnant magnetization in both bilayer case and a monolayer. But if you subtract, for example, the saturated magnetization and the magnetization at zero, and you only get the bilayer area give you a signal, and the monolayer disappears. So we can actually use this quantity, magnetization at the zero field and the saturated magnetization to sort of describe the relative area of ferromagnetic domains. So if you look at this, looks like about half is ferromagnetic, the other half is antiferromagnetic. Okay, so let's put the results from different samples together. So what I'm showing here is the percentage of ferromagnetic domain as a function of twist angle from 0 to 60 degrees. After 60, you repeat because of a threefold rotation. And at the bottom shows, and you can see here, there is a kind of a step change around 3 degrees. So for twist angle larger than 3 degrees, everything is ferromagnetic. Below 3 degrees, you have mixture of ferromagnet and antiferromagnetic response. And the spin flip transition field pretty much is a constant. So how do we understand something like this? I told you for rhombohedral stacking, it should be ferromagnetic, and for monoclinic, it should be antiferromagnetic. And the ferromagnetic interlayer interaction actually dominates. This is bigger, this energy is bigger. So that's why at the larger twist angle, everything is ferromagnetic. But if you are at a smaller twist angle, it is possible that you break into domains. And then somewhere in the middle, there should be a transition. And you would expect to have some non-collinear phase coming out. So, and that's this area. So we are looking at two competing energies. We gain a little bit energy for forming antiferromagnetic domains in this monoclinic region, but we need to pay energy for forming domain walls. So if you look at the energy for forming antiferromagnetic domains, and that's proportional to the area of monoclinic region, right? So it's proportional to size of the Moray pattern square. It's the area, right? And energy cost for forming domain walls is proportional to length of the superlattice. So it's linear proportional to that. And then at the transition, you just need to balance the gain and the cost. And you can imagine, for very large Moiré pattern, the area always wins. So you get antiferromagnetic and ferromagnetic, so the non-collinear case. And for a smaller Moiré pattern, you only get into ferromagnetic. And that also gives us a critical angle. I see I probably should have tried to finish up. Is that right?
Okay, so 1 minute.
Okay, good. Okay, so I have one more slide to show, so and that explains this critical angle, right? And then if you look at this, the critical angle is controlled by interlayer interaction. So if you can tune this and you sit at a fixed twisted angle, you should also be able to see this phase transition, right? And this is something we tried. So we add electrostatic doping to the bilayer, and that will weaken the outer plane field if you electron dope it. And then you can see that when you change the gate voltage, the remnant magnetization becomes bigger. And if you look at the fraction, actually, if you dope more and more electron, it is possible that we haven't demonstrated yet, to induce non-collinear state to ferromagnetic state quantum phase transition. So I think I should stop. I will just show my summary here, and I'll be happy to answer questions if you have any.